Let's take a look at this problem here. We're given a rectangular sheet of cardboard or some material. I forget from the problem what they state it is. And the dimensions for the one I had are 19 feet by 11 feet. Your dimensions, again, may vary depending on the problem. But you're going to take this piece of cardboard or whatever it is, and we're going to cut out squares out of each of the corners here. And I'm letting X be the side length of each of these squares. They're all exactly the same. And you see I've done this dashed line. What we're going to do is after we cut out those corners, we're going to fold these flaps up and form a open top box. Okay. And the question asks us to find the value of X, which is the side length of the square, um, to well, actually, they want to maximize the volume. You have to find the value of X needed to maximize the volume, but they want the actual maximum volume. First of all, note that when I fold these up, what's the side length of my box going to be? Well, the total length here on this side is 11 feet, and then each of these squares are a length of X. So I'm taking away X plus X, or 2X. So 11 minus 2X is this side length. And then this other side length will be therefore 19 minus 2X. And then when we fold up these flaps, the height will be X, right? Because that's the side of the square that we're cutting out. Okay. I'll further note that the value of X must be greater than 0. Otherwise, we still have just a sheet of cardboard here and can't make the box. And it has to be less than 5.5. If we're X is 5.5 feet, that means each of these squares will be 5.5. Then notice that the 5.5 plus 5.5 is 11. We would just be cutting off, 2 squares out of that, and we would be left with another sheet of um, cardboard that was 8 feet by 11 feet. So this has to be the restriction on our values that we want to talk about. So keep that in mind. Okay, what's the volume of any box? It's the length times width times height. So I multiply those together. And then to maximize, right, what am I going to do to maximize this function? I'm going to find the critical values on this interval. And then I'll need to do, in this case, a sign check to confirm that I have a maximum at the critical point, any critical point that I find. So what I'm going to do here is distribute this out, expand this out, FOIL this out, multiply by X, and we get this as our function. Again, with this restriction on X. Finding the derivative is pretty easy for a polynomial function. We get this for our derivative, right? And then to find the critical value, I want to find when the derivative is 0. This requires us to solve this quadratic equation here. This is not something we can factor, not a very pretty thing. I'm going to go ahead and use the quadratic formula. Notice the value of A is 12, the value of B is negative 20, and the value of C is 209. So I just plug that in. Remember, X is negative B plus or minus B squared minus 4AC under the radical divided by 2A. So just evaluating those, of course, we get down to this. And then using the calculator, you'll get 2, right? 120 plus this square root divided by 24 and 120 minus. Here's our 2 values. But remember, this one is not going to be valid because remember the value of X has to be between 0 and 5.5. So this is our only critical point of interest. And we will need to do a sign check to show that we have a maximum. It's about 2.25. And if I check a value of my derivative for any value between 0 and 2.25, like 1, if I plug 1 into this derivative, I'll have 209 minus 120 plus 12. Well, that's going to be a positive number. So I have positive there. And if I plug in something between 2.25 and 5.5, like 3, if you plug that into the derivative here, you will get a negative number. This means what? That because our derivative is changing from positive to negative, the function must be increasing and then decreasing. So we indeed have a maximum at 2.25. So the question of the problem was, what is the actual maximum volume? So I want to plug this value into the formula for my volume, which is up here, and that will give me the volume. Now, when you're doing this in the calculator, let me show you what I did. Um, so in finding the root here, I did the 120 minus the radical divided by 24. That gave me this value here. Don't round that off. I mean, I know I rounded it off down here in the sign check, but don't round that off. That's why I'm emphasizing plugging in the whole thing. I just used the answer feature in the calculator and went up here to the actual volume, right? 209 times answer, right? Which is this value unrounded minus 60 answer squared plus 4 answer cubed. And we got that. When you finally get the final result, then round off 212.06. So there's some tolerances, but you can't round off intermediate results. You need to keep everything unrounded until the very end. Okay, this was just part A of the problem. Part B was to do basically the same problem, but this time imagine that our sheet of cardboard is a square with an arbitrary side length of S. And so now my picture is going to look like this. I don't know what S is, but it's some positive number, right? And both of these sides are the same because it's now a square. I'm still cutting out the little X by X squares, folding up the flaps. Notice this gives me a box that looks like this, very similar to the one we had before, but this time it's each side is the same. S, take away two X's. So S minus 2X, S minus 2X, and again, the height is X. Notice the value of X has to be greater than 0 and less than half of S, right? If I cut out the squares half of S, I'm just going to cut this square into 4 smaller squares, right? And not be able to fold up and form this box. The volume is base times width times height, which gives me this. If I expand S minus 2X squared, what do I get? I get S squared. The outer and inner would be what? Negative 2SX, which gives me a total of negative 4SX. And the last, negative 2X times negative 2X is positive 4X squared. Distribute that X through. That gives me my volume as a function of X. Keep in mind, S is a constant. S is not a variable. S is the length of the side. So S is 10 feet. S could be 12 feet. S could be 20 feet. We're just going to get a answer in terms of S. So what are we going to do to maximize this? We're going to find critical points. So I take the derivative, remembering S is a constant. So this is 12X squared. 4S is a constant. Bring the 2 down. I get negative 8S times X to the first power rule. And remember, S is a constant. S squared is a constant. So any constant times X, the derivative is just that constant, right? S squared. Okay, so derivative now is 0. What's our critical point when this thing is 0? Now, I'm going to use the quadratic formula again, but keep in mind S is a constant. So the coefficient of X squared is 12. So A is 12. What's the coefficient of X? That's B. Well, it's not negative 8. It's negative 8S, right? That's the value of B. It's dependent upon S. And notice C is S squared. Okay? So I've got negative B plus or minus B squared minus 4AC, all under the radical, divided by 2A. So down here I got 24. This becomes positive 8S. This becomes positive 8 squared is 64S squared. And this is 4 times 12, 48S squared. So when I subtract, I get 16S squared. Well, that's nice because the square root of 16 is 4, and square root of S squared is S. So this is just 4S. 8S plus 4S would be 12S over 24. 12 24 is 1/2. Notice that this is not going to be a possible situation because we said what? The value of X had to be less than S divided by 2. So that's not going to work. If we do 8S minus 4S, we get 4S divided by 24, which is 1/6 S, or 6 divided by S. Okay. Do we have a maximum at that value? Well, we need to do a sign check. The sign check is a little tricky here. Again, from 0 to S, 1/2 S is the interval we're interested in. 1/6 of S is here. We know the derivative is 0. If I plug in something between 0 and 1/6 of S, what could I do? Well, if I take the average between 0 and 1/6 s, I get 1/12, right? 1/12. And what I did is I want to look at the derivative up here and evaluate it when s is, or when x rather is 1/12 of s, or s divided by 12. So I just replace x with s divided by 12, x with s divided by 12, and I simplify. So I get 12 times what? S squared over 12 squared, s squared over 144, but 12 divided by 144 is just 1/12 s squared. This will be s times s squared, 8/12, right? We can simplify that down to 4/3, but I'm going to leave it as twelfths because I've got this over twelfths, and 1s squared would be 12/12 of s squared. Just makes it easy for me to add these together, right? They're all like terms, so I just add their coefficients. 1/12 minus 8/12 is negative 7/12 plus 12/12, 5/12. Bottom line is, for any value of s, obviously this will be a positive number. And that's why in my sign check, I have positive here. Over here, we could check, I just took the average between 1/6 of s and 1/2 of s, and that is 1/3 of s. Okay, in other words, this is 1/6. This would be 1/2, which is 3/6. What's halfway between 1/6 and 3/6? Answer, 2/6, which is 1/3. So when I go back to my derivative here and plug in 2/3 for x, sorry, s, 1/3 s for x, I get the following. And very similar to what I did up here, I simplify this out. And when I simplify it, I get negative 1/3 s squared. Well, for any value of s, this will always be negative, less than 0. And so this is negative. Bottom line, derivative changes sign from positive to negative, so we have a maximum at s over 6. What is that actual maximum? Well, I need to find the volume, and remember the volume was this, 4x cubed, right? All this stuff. I'm going to replace x with 1/6 s, or 6 divided by s. So it was 4x cubed, so replace x with that, minus 4s x squared, and then plus s squared times x. So when I do 4 divided by 6 cubed, that simplifies to 1/54 s cubed. And this will be 4 divided by 6 squared. 4/36 is 1/9. Of course, it's negative 1/9. And then this will just be 1/6. And notice it's s cubed. S times s squared is s cubed. S squared times s is s cubed. So they're like terms. We just add them together, and we get 2/27 s cubed, or 2s cubed over 27. So basically, the volume of the box will be maximized when the value of the uh, x that we cut out is 1/6 of the side length, and the final resulting volume of the box will be 2/27 times that side length s of the original square cubed. Okay, kind of involved problem there. Very interesting though. Hope this helps.